Hello and welcome to today's lecture on MOS inverters driving large capacitive loads. In the last three lectures, we have discussed various characteristics of MOS inverters, their configuration, what are the different ways by which you can realize MOS inverters, their characteristics, voltage transfer characteristics, then your switching characteristics. And today I shall discuss about how MOS inverters can be used to drive large capacitive loads efficiently. And this is the agenda of today's lecture. After giving a brief introduction, I shall discuss about various techniques which are used for driving large capacitive loads. Number one is use of super buffers, second is use of BiCMOS inverters, third is buffer sizing. So, we shall discuss all these techniques one after the other. Coming to the introduction, there are situations when a large load capacitance such as long buffers, off size capacitive load or IO buffer are to be driven by gate. See, you are realizing different circuits by using VLSI technique, but you have to drive some off chip loads. For example, if you are realizing a system, so output will go from one chip. Say this is your chip 1, it will go to another chip. So, what is being done? There is a package in which this chip is available, and this chip is also available in another package, and through bonding pod connections are taken to the pins, and from the pins connections are taken. So, whenever you are taking such connections outside the chip, the load is very high, that means capacitance is very high. Capacitance is high. How much high? As you know, normally in the based on the present day VLSI circuits, the parasitic values of different capacitances, which I have mentioned in my previous lectures, are of the order of femtofarad. On the other hand, these off chip loads are of the order of picofarad. So, you can see there are several orders of magnitude higher capacitive loads the circuit faces whenever it has to be taken outside. Similarly, you will require some long buffers, you have to drive very large number of outputs whenever it is within the chip. For example, the fan out is very high, you are driving. So, this is coming out from a chip gate and it is going to say a large number of other gates. So, large fan out, here also capacitance is high, but not as high as the off chip capacitance. This is your off chip. So, whenever you are driving such high capacitive loads, the delay can be very high if driven by standard gate. What do you really mean by standard gate? Standard gate means the gates realized by using minimum dimension. As you know, for a particular technology, lambda is the minimum resolution that is permitted by a technology, then 2 lambda is the minimum feature size. So, normally you can realize a length is equal to 2 lambda, width is equal to 2 lambda, etc. So, L by W, if it is 2 lambda by 2 lambda for a particular technology, then we say that it is of minimum dimensions. So, whenever you are realizing an inverter using this kind of minimum dimension, we call it, or maybe a little bigger than that when we have to use little larger, the L by W values may be little different from minimum values, then we call it standard gate. So, and if the load is very high, and as you know, this in such cases delay is proportional to CL. In the last lecture, I have derived an expression where it has been mentioned that delay is proportional to CL. So, whenever this is 3 orders of magnitude compared to the parasitic capacitances, within the chip, then the delay can be several orders of can be very high. So, in such a case what can you do? We have to develop technique such that the delay can be minimized. Obviously, delay cannot be, delay will be there, our objective will be to minimize it. To how this can be done, let us look at the limitations of the standard gates. First, let us consider a simple NMOS inverter. We are starting with NMOS inverter because that super buffer which I have mentioned has been introduced essentially in the context of NMOS inverters. So, how do you realize a NMOS inverter? NMOS inverter, the best possible configuration as we have seen can be realized by using a NMOS depletion type transistor as pull up here, and this is connected to the source, this is VDD and this is connected to ground, and here you apply input voltage and here you take the output voltage. So, in such a case, as you can see, we are using a standard NMOS inverter, where as you know there are two problems. Number one problem is asymmetric drive capability of pull up and pull down devices because of ratioed logic. As we know that L by W ratio has to be 4:1 minimum, and whenever this is 1:1, that means you have to maintain a ratio between the L by W ratio of the pull up device by the pull down device. So, whenever this is a situation, there is a asymmetric behavior in the switching characteristics, and whenever you are charging and discharging a capacitive load, that means it has to be charged through this device having length is equal to 4 into 2 lambda compared to here it is only 2 lambda, length is 2 lambda. So, that means resistance of this device is at least 4 times that of the pull down device. As a result, the TP low to high is large compared to TP high to low. So, high to low, low to high is larger than the high to low. So, high to low it is getting discharged here. So, because of the ratioed logic, this is one problem. What is the second problem? Second problem is when the pull down transistor is on, the pull up transistor also remains on. You see, normally the resistance of this device is small. So, the discharge time will be shorter, but unfortunately it has to fight two enemies. What are the two enemies? Number one is the current that is being supplied by this pull up device, because that transistor is always on. So, that current has to be will also pass through the pull down device when the capacitor is getting discharged. That means, this current and also the current that is required to discharge these capacitors. So, this pull down device has to sync the current of supplied by the pull up device and also the current required to discharge this capacitor. And as a consequence, whenever this TP high to low also is affected because of this, and it is also not very small, and as a consequence delay is very large. So, question naturally arises, is there any way by which these two behaviors, these two problems, number one is asymmetric behavior, number two is the pull down device has to sync the current of the pull up device when the output is going from high to low. So, that is where we shall introduce super buffer. Super buffer will overcome these two problems. Now, coming to limitation of driving by a simple CMOS inverter. So, in case of CMOS inverter, fortunately that asymmetric behavior can be overcome to such extent by using devices of proper size. We have seen that. You see, this is a CMOS inverter. Here at least the second problem that does not arise, that means when this transistor is on, this transistor is off, and as a consequence the pull down device need not really sink the current supplied by the pull up device, because pull up device turns off. So, that is the advantage of CMOS inverter, but unfortunately what happens whenever this is driving another stage, you can see here the capacitance is quite large compared to NMOS, because in case of NMOS this stage will be driving only the, it will go only to the NMOS transistor. The PMOS transistor, if it is an inverter, you can see, sorry, if it is a, this will be like this. So, it will go to only the gate. So, gate of the NMOS transistors. As a result, the capacitance of this will be much smaller compared to capacitance that will be faced by a CMOS inverter. So, you can see here it has to drive the PMOS transistor and NMOS transistor. As you know, to have symmetric characteristic, the width of for this device has to be 3 times, that means W by L ratio. If we write, this has to be 3:1 and this will be 1:1. So, that means the capacitance that it will face is 4 times that of a NMOS inverter. So, we can see that CMOS circuits, although the current drive capability is little larger, but the capacitance is also larger, and as a consequence it has been found that the delay of a NMOS inverter and a CMOS inverter is comparable. That means, in case of CMOS inverter you are getting more drive capability, but the capacitance is larger, and as a consequence the CMOS inverter is not really very fast. That means, the NMOS and CMOS inverters have comparable delay characteristics. So, question naturally arises, how can you really minimize the delay in case of a CMOS inverter? So, for that purpose we shall see one solution has been provided, that is use of BiCMOS inverter, BiCMOS. As you know, bipolar transistors have very large current drive capability, but they suffer from lower input impedance. On the other hand, CMOS has higher input impedance, because input is applied to a gate, and where because of the presence of silicon dioxide, that input impedance is high. How to get best of both the worlds? So, high input impedance of NMOS, larger driving capability of bipolar devices. That is what is being achieved with the help of BiMOS inverters. That means, here you will see we shall combine bipolar transistors and CMOS devices, that means CMOS inverters, to realize BiCMOS inverters to achieve lower delay. Then finally, another technique we shall discuss, that is your cascaded stages. We shall see that instead of using a single large driver, it is more beneficial to use several inverters or drivers of increasingly larger size to reduce the delay. Later on we shall discuss about it, that is called the cascaded driver stages of increasing stage ratio. So, these are the topics I shall discuss in this lecture, and let us first discuss about super buffer realization. As I mentioned, to alleviate the problem of large delay of NMOS inverters, super buffers have been introduced. So, what is being done in a how the super buffer is realized? So, this is a inverting type super buffer. As you can see, what has been done, you have got a standard NMOS inverter, as you can see, and that a standard NMOS inverter is driving 2 transistors. But you can see here these 2 transistors is driven in such a way, one input, I mean the pull up device is being driven by the output of this inverter, and pull down device is driven directly by this inverter. What is the benefit that we get from here? Let me redraw the circuit to explain its operation. So, as you know, this is a standard NMOS inverter. So, what has been done? Here you apply the input voltage. We have used 2 more transistors, obviously one pull up and another pull down, but instead of connecting the gate of this NMOS depletion type transistor, this is connected to the output of the first stage of inverter, and then input is applied directly to this. Now, let us consider 2 different situations. Let us assume here we have applied VDD. Let us assume we are using this ratio, W by L ratio, 1 is to 2, 2 is to 1, 2 is to 1, 1 is to 2, W by L ratio are mentioned here. Now, in such a case, what will be the how the circuit will operate? Let us assume your input voltage is equal to 0 volt. When the input voltage is 0 volt, what will happen? This particular input will be 0. So, this transistor, let me write down the transistors Q1, Q2, this is Q3 and this is Q4. So, in this case Q3 is off. What about Q4? You can see here what is happening, this input is 0, as a consequence this transistor is off, and obviously here you shall get large drive to this transistor. That means, the drive to this transistor is quite large, and because here it will be very close to VDD. Of course, yeah, it will be VDD only, because this transistor will remain on throughout. As a result, the applied it will apply VDD output to the input of this particular transistor. As a consequence, Q3, Q4 is on. Not only on, Q4 gets large drive. Why I am telling large drive? Why large? The reason is, normally this gate is connected to source. So, gate to source voltage is 0, but here you can see in this particular case it is not true. This is connected to VDD. As a consequence, the charging time will be quite large. I mean, sorry, charging time will be quite small, because it is getting large drive, and current supply that will come from this NMOS depletion type transistor will be large. Now, let us consider V in is equal to VDD. In this case, what will happen? Q3 is on. What about Q4? In this case, as you can see, whenever this is VDD, this is on. So, here what will be the output? Here you will get, it will generate a output which is equal to 0. So, whenever you are applying a 0 volt here, what will happen to this transistor? This transistor will turn off, because with respect to this, this is on, this transistor is on. So, here this transistor will be on, and as a consequence what will happen, this transistor will turn off, Q4 will turn off. So, what is happening now? The Q3 need not really sink 2 currents, one coming from the pull up device, another coming from the capacitor. So, as a consequence, this discharge time also will be faster. That means, in this particular gate we can see the gate the pull up device is driven by a signal of opposite level of the pull down device generated by a standard inverter. The gate of the pull up device of the super buffer is driven by another inverter with about twice the gate drive, as I have already explained. Thus, the pull up device is capable of sourcing about 4 times the current of the standard NMOS inverter. Normally, as you know, because of the ratioed logic, we get 1/4 current, but we can see here because of this larger drive, it will be able to supply large current. That we can really explain by, we can really do some computation. Let us do some computation about the two cases. One is your standard inverter, another on the other side we shall compute the super buffer. So, how the currents of these two are different. So, first of all, as you know, I ds saturation that is equal to, as you know, beta pull up by 2 V gs minus V T dep, where V dep is equal to roughly about minus 3 volt. You know, this PMOS transistor, the depletion type transistor will turn off when you apply minus 3 volt. That is why this is the voltage. In such a case, if we substitute the values, we shall be getting this is equal to beta pu by 2 into this voltage is 0 now, when the input voltage is 0. So, 0 plus 3 square. So, that is equal to roughly 4 point, that means 3 into 3 9 by 2 4.5 beta pu. So, this is the current that is being supplied by the transistor whenever it is in saturation. What about the current whenever it is in the linear region? Then this is equal to beta pu by 2 beta pu by in this case it will be VGS minus VI V TDP minus VDS square by 2. So, this is the expression for linear region. In this case, if we substitute various values, say VDS is equal to of course, here there will be VGS, VDS, another term will be there, and because we have taken the VDS inside. So, if we substitute various values, we will find that this is equal to roughly 4.38 beta pu. That means, so in case of standard inverter, the current drive is like this. That means, partially this particular inverter, when it is charging this capacitor, part of the time it will be in saturation, part of the time it will be in linear mode. I mean, sorry, this particular transistor, part will be the time it will be in saturation, part of the time in the linear mode. As a consequence, the average current if you take up, which will be equal to, if you take the average, this will be roughly equal to 4.4 beta pu. This is the average current that will be supplied for pulling the device on. That means, the source current for a simple inverter. Now, let us consider in case of super buffer. So, in case of super buffer IDS, whenever you are applying 5 volt, so that time what is the drive, because it is getting the drive of 5 volt whenever you are charging this capacitor. So, that time it will be voltage will be beta pu by 2 into 5 plus 3 into 5 minus 5 square. It is in the linear region, that is why this is the expression, and this we get 27.5 beta pu. And whenever IDS is equal to 2 volt, that means we are assuming that this output is changing. So, initially it was 5, then it will come down to 2, then we shall take the average. So, when it is when the output voltage is 2 volt, that time beta full up by 2, again 2 into 2.5 plus 3, sorry, not 2 volt, I have taken 2.5 at the middle point, into 5 into 2.5 minus 2.5 square. So, this if we calculate, it will be equal to 10.62 beta full up. So, if we take the average of the two, we will be getting 27.5 plus 10.62 by 2. So, IDS average will be equal to 27.5 plus 10.62 by 2 beta pu. So, this is roughly equal to 19.06 beta pu. As I was telling that it will be about 4 times. So, 4.4, that is the standard inverter, 19.06 for the super buffer. So, we find that driving capability is quite large, and as a result that asymmetric characteristic is no longer present. And of course, I am not there is no problem about discharging, because the resistance is length is small, as you can see 1/4, and as a consequence the discharge time has not been considered, but it is more or less comparable for both the cases. But in this case also it is getting discharged by the same type of same transistor of the same size, here also the same thing. So, there is no difference so far as the discharge time is concerned, but asymmetry was present only for the charging time, and that is being alleviated with the help of super buffer. So, this is roughly equal to 4.3 times of a standard inverter. So, this is the super buffer. Now, let us consider non-inverting type. So, previous one is the inverting type, because whatever input you apply you get the inverted output here. But in this particular case the connection is done in a little different way, only instead of applying this input to this pull down device, the input is applied to the pull up device, and output of the inverter is applied to the input of the pull down device. So, this converts the inverter into a non-inverting type super buffer, and obviously the characteristics will be similar to what I have already discussed. So, we find that the super buffer can be realized both inverting type and non-inverting type, and that overcomes some of the limitations of standard NMOS inverter. Okay. So, this is the use of super buffer. Now, we shall come to the second topic, that is your BiCMOS inverter. As I mentioned, the CMOS is, although it is good, but its delay characteristic is not very good. I have already mentioned that, because of large capacitances. So, this can be modified to realize a BiCMOS inverter by adding both bipolar and bipolar devices and CMOS devices. How it can be done? So, let me draw a BiCMOS inverter. Actually, you can have different types of realizations of BiCMOS inverter, but I am considering the simplest and the most standard one. So, this is the diagram of that. You have got the basic inverter is here. This is connected to VDD. Now, this output is driving a bipolar transistor. So, you can see this is a NPN type transistor VDD. So, instead of driving using a MOS transistor, a bipolar transistor is used. Of course, you will have a kind of push pull realization. Push pull realization means you will be having two devices. So, when one is on, another one will be off. So, here also you will require two transistors. So, here are the two transistors, bipolar transistors, but you can see both are NPN type, and then this is connected to ground. What is being done? We have to realize in such a way that when this is on, this is off, and when this is off, this is on. To do that, we shall be using another few additional transistors. This is connected to the base of this transistor, and this is connected to the output, and this one we have got another transistor here, NMOS transistor. This is connected to this particular line. So, we have got how many devices? So, you have got two bipolar transistors and 4 MOS transistors, and these are, say, this is your P1 P type transistor, this is N1 NMOS transistor, this is N2, this is N3, and here you are applying input, you are taking output from here, this is your V out. Now, let me explain the operation of this bi-CMOS inverter, how it really works. Let us assume V in is equal to 0 volt. So, when V in is equal to 0, as you know, this P1 will be on, P1 is on, N1 off. I shall discuss about N3 and N4 little later, and what about this makes whenever P1 is on, what is the voltage here? You will get VDD. So, this will make N3 on. What about this transistor? Since V in is equal to 0, N2 will be off. So, these are the states of these 4 transistors. Now, what about these 2 transistors? Since P1 is on, the drain current of this transistor is will pass through this Q1 transistor, and as a consequence you can see here you will have a large base current. So, this will be the base current, the drain current of P1 is the base current of Q2, and obviously Q2, if it is having beta of 100, the current that will be able to supply is 100 times that of the drain current of the PMOS transistors. So, it will be able to supply very large current. Okay. So, Q1 is on and it can drive, it supplies large current. That means, the pull up time will be quite fast. Now, let us see whether this transistor is off whenever this is on or not. Otherwise, you know, this transistor has to fight with this transistor to drive when driving this, because some of the current that it will supply will pass through, will be bypassed by this transistor. So, whether this is prevented or not, let us see. What happens in this particular case? In this particular case, as you know, this N3 is on, as you have seen. So, this N3 actually clamps the base of this Q2 transistors. That means, the Q3 is acting as a kind of clamping device. It actually the base of the Q2 transistor is clamped to almost 0 volt. So, what will happen in that case? Q2 will be off. As you know, this is a silicon transistor, bipolar transistor. To make it on, you will require 0.6 volt. So, whenever the voltage here is 0, base to emitter, then this will be off. So, this makes Q1 off. As a consequence, the Q1 need not fight with Q2 while driving this capacitor. So, that means there will be no current, no current will pass through Q2 when Q1 is on. Now, let us consider, so this is one situation. What about when V in is equal to VDD? When V in is equal to VDD, then what will happen? Let me write down the state of the different transistor. P1 is off, P1 will be off because this input is VDD, N1 is on, N2, what about N2? N2 also will be on, N2 will be on. And what about N3? N3 is off. Okay. So, now how the state of these 4 transistors affects the bipolar devices, let us see. So, whenever P1 is off, this particular device does not really get any drive, it does not really get any drive. But what happens at that time, this transistor, this N1 transistor, the transistor N1 is now on. So, what it will do? It will act as a clamping device N1. So, that means Q1 is off. So, Q1 will be off because this voltage will be pulled to 0 volt, it will by making this transistor off. What about Q1, Q2? Q2, as you can see, this transistor is on. The drain current of N2 will pass through base of this transistor Q2. That means, the drain current of N2 will now be will now supply the base current of Q2. As a result, the current drive for this Q2 will be large. That means, it will be able to discharge this capacitor with a large current. And as a consequence, this we have seen the role of N3 essentially to clamp this output, role of N2 supplying current when this transistor is on, role of N1 and N2 we have seen. So, these 4 transistors actually ensures the push pull behavior of Q1 and Q2. So, by ensuring that, we are able to not only drive large capacitive load, because the current that can be supplied by the bipolar transistors Q1 and Q2 is very large, and when Q1 is on, it is ensured that Q2 is off, and so on. So, we have seen the behavior. Now, let us consider the characteristics of a bipolar inverter, this BiCMOS inverter. Let us consider the transfer characteristic. Transfer characteristic. First, let us consider the compare it with the transfer characteristic of a NMOS inverter, a CMOS inverter. As you know, in case of a CMOS inverter, the transfer characteristic is somewhat like this. So, this is VDD, almost near the middle this transition take place, and slowly it goes, as you know, it can be divided into 5 regions. This is your VTN, this is your VTP, and this is VDD by 2 roughly, and starting from sorry, the VTN will be somewhere here anyway, not this one. So, it starts current starts flowing, and for this entire duration this is actually VDD minus VTP, this point. So, we know that slowly the transition occurs because of the relative value of the P and NMOS transistors. We have already seen that, discussed about it in detail. What change that will take place in case of BiCMOS inverter, the transfer characteristic? Unfortunately, in case of bipolar BiCMOS inverter, you will not get VDD, at the output. Why will not get VDD at the output? The reason for that is this transistor has some drop when this is in saturated condition. So, this will be in saturated condition. So, there will be some voltage drop across it, although it will be small, not very large, but it will have some drop. So, what will happen? Here the transition will occur very fast, not like this one slow, and then it will remain, it will be somewhat like this. That means, the transition will occur very fast, but it will not also not go to 0. Why it will not go to 0? Again there will be a voltage drop across this transistor VCE, that is not 0 in case of the bipolar transistors, and as a consequence you are getting this VCE sat VDD minus VCE sat here, this part. Similarly, here we are getting VCE sat of the pull down device. So, we find that there is some voltage drops, small voltages here, but transition will be very fast because of large switching. So, this is the transfer characteristics of this is for CMOS and this is for BiCMOS. Now, let us study another behavior, how the inverters behave whenever you change the fanning, whenever you change the fan outs, not fan in, fan out. What is fan out? Fan out is, say here is an inverter. Inverter will be driving several loads. It can, if it drives only one gate, then fan out is 1. If it drives 2 gate, then fan out is 2. If it drives 3 gate, then fan out is 3, and so on. That means, as the fan out increases of this particular gate, then the output capacitance also increases, because the this capacitance value that it will face as load capacitance will keep on increasing. So, you can do an experiment. You can study the switching characteristics for different values of load capacitance or different value of fan out by adding one gate, adding another gate, adding another gate, then you can measure the delay. So, on this we shall be measuring the delay, and here it is fan out. So, it is increasing from 1, 2, 3, 4, 5, 6, 7, 8 and so on. So, if fan out is increasing 1, 2, 3, 4, 5, 6, 7, 8, let us assume, and how the delay will increase. Let us assume this is the delay characteristics of a CMOS inverter. So, this delay will be in picosecond. In what way it will be different in case of BiCMOS inverter? In case of BiCMOS inverter, it has been found that delay characteristic will be somewhat like this. That means, delay will definitely increase, but for CMOS inverter it will increase at a faster rate compared to standard CMOS inverter. This is for BiCMOS and this is for CMOS, standard CMOS. Now, you may be wondering initially why delay is more for BiCMOS compared to standard CMOS. Initially, for fan out of 1 or 2, delay is larger for BiCMOS compared to standard CMOS. Why is it so? The reason for that is, you can see BiCMOS inverter is a little complex. So, this particular inverter is driving this transistor. So, the path delay will be little larger whenever the load is small compared to if you take the output from here. That means, compared to a simple inverter, for a BiCMOS inverter delay will be larger, because it has essentially got 2 stages, and here also it will be having 2 stages. But as the fan out increases or the load capacitance increases, then as you can see, ultimately BiCMOS inverter is becoming faster compared to standard CMOS. So, you see this is for experiment with VDD is equal to 5 volt, and it has been carried out for different dimension. You can see here it has been assumed that for CMOS WP is equal to 15 micron, WN is equal to 7 micron 2 times, and for the BiCMOS WP is equal to WN is equal to 10 micron, and WQ1 is equal to WQ2 is equal to 2 micron. So, that means these are the dimensions of the bipolar transistors, whereas these are the dimensions of the PMOS and NMOS transistors. So, we have studied the delay characteristics of a BiMOS inverter compared to standard CMOS. Okay, now let us switch gear and come to the last topic, that is your buffer sizing. You can see here an experiment has been carried out to see the normalized delay for different fan out and different sizing factor. What do you mean by sizing factor? Sizing factor is essentially how big is the width. Say for the standard minimum size gate, width is 2 lambda. We are not changing the length, we are increasing the width to reduce the delay, because it will reduce the resistance. So, the delay is the fan out, the sizing is increased, that means width of the P and NMOS transistors are made 1.5 times, 2 times, 2.5 times, 3 times, and so on. As you do that, how the delay changes? We can see that whenever the fan out is small, say 3, then as you increase the size, it definitely reduces the delay, but not to a great extent. Reduction is 20%. You can see this is a little more than 20%, say 25%. But when the fan out is large, say 8, we have done experiment for fan out 3, 4, 5, 6, 7, 8. That means when the fan out is 8, then you can see as you increase the size, delay reduces significantly. So, this is the delay is 50% of that of the initial condition. That means whenever the fan out is large, by increasing the buffer size, you can reduce the delay. When the fan out is small, there is no significant gain. So, usually sizing is not done. So, sizing has been found to be a very important technique by which you can reduce delay. Obviously, in this world nothing is free, the area increases. So, you are trading area for smaller delay, you are paying the price in terms of area. As you are increasing the size, the dimension of the devices will increase, that will increase the area. So, at the cost of the area, you are reducing the delay. So, in the present day high performance circuits, delay may be more important than area, because of the reduced increasingly reduced dimensions. You have abundant space for fabricating millions of transistors, but you want higher performance. So, what can be done? You can trade area for delay. That is the reason why sizing is a very important technique for reduced delay. Okay. Now, let us now consider a situation in which a large capacitive load like output pad is to be driven by a MOS gate, and as I have already mentioned, typical value can be of the order of 100 picofarad. So, it is quite large. So, if such a load is driven by a MOS gate minimum dimension, then delay can be 10 to the power 3 tau. So, let me first introduce this term tau. What is tau? Tau actually is called the unit of delay. Whenever you are driving an inverter of minimum dimension, another inverter of minimum dimension, then whatever is the delay, because here you can see the resistance is decided by the W by L of this, and capacitance is also decided by the W by L. So, assuming that they are of minimum dimensions, then whatever is the delay for driving a gate of unit dimension, minimum dimension, by gate of another inverter of minimum size, whatever is the delay, we call it tau. With respect to this tau, we shall compare the delay whenever, say, let us assume we have to drive a large capacitive load. Say this capacitance is 1000 times that of Cg, the gate capacitance together of this. So, compared to this is 1000 times. So, what will be the delay? You see the capacitance is larger, resistance is same as this. So, as it can be proved that the delay will be equal to 1000 tau. Now, you may say, okay, now what I shall do, I shall put an inverter and then a large inverter with width is equal to 1000 times that of the standard minimum gate. So, in this case, what will be the delay? Again, this is 1000 Cg. What will be the delay for this? So, here it will be facing a capacitance of 1000 Cg, again, because here you have put the dimension has been made 1000 times larger. So, delay of this gate will be again 1000 tau maybe, but the delay of this gate will now reduce, it will become tau, because resistance is now very small and you are driving the capacitance. So, because the relative value of resistance and capacitance is dependent. So, that means the total delay will be 1001 tau in this particular case. Now, let us consider a situation where instead of doing this, let us increasingly change the size. So, here it is 1:1 inverter ratio, this is 10:1, here it is 100:1, that means with respect to minimum dimension. What has been done here? This is this inverter of minimum size, this is the size of this is 10 times that of the minimum size, and the size of this is 100 times to that of the minimum size. So, what will be the delay, total delay in this particular case? So, here how much capacitance is faced? 10 Cg. Here how much capacitance it will face? 100 Cg, and here as we have seen, we have put a capacitance of 1000 Cg as the original. So, what will be the delay of this? 10 tau. What will be the delay of this? What will be the delay of this? So, we find it is 30 tau compared to 1000 tau. In this particular case, we are finding 1001 tau, in this case we are getting only 30 tau. This is a significant reduction. So, question is, by having a cascaded stage or stages of inverter, we can reduce the delay significantly. Question is here the question is how many stages and what will be the increasing stage ratio. You have to optimize it. I have illustrated this with the help of stage ratio of 10, but is this delay minimum? Can we achieve still lower delay? That can be done. How it has been done? We have decided to get optimal stage ratio. So, you can find out what is the delay. This is the delay n f tau. You have used n stages with stage ratio of f. F is the ratio of the CL by I mean that gate capacitance of the first stage by the minimum gate capacitance. So, n f tau is the value of this, then we can differentiate it and make it equal to 0. You know, whenever you have to get the minimum value, the standard practice is to differentiate it and equate it to 0, and if you do that, we get the value of f stage ratio is equal to E. So, T minimum, that is the minimum value of delay that we will get, is equal to n f tau, where n is the number of stages, f is the stage ratio and tau is the unit delay as we have seen. So, it is E tau ln CL by CG. CL by CG is the CL is the load capacitance and CG is the gate capacitance. So, with this this is the minimum delay we are getting. Unfortunately, this value of f is equal to E is quite small. It is equal to 2.7. So, with this value of stage ratio, you will require large number of stages. What is the effect of this large number of stages? Effect of large number of stages is when minimum delay with f is equal to E will lead to large number of stages, and when n is large, then it will lead to larger area. So, is there any way we can do some optimization of the area? To do that, let us look at the delay characteristics for different stage ratio. We find that although it is minimum for f is equal to 2.7, but it does not really increase very quickly, it changes slowly. So, we can see if we take say stage ratio of 4 to 5, then there will be small increase in delay, but small increase in delay, but that number of the stages required will not be very high, and as a consequence the delay, the area will be smaller. That means, instead of choosing stage ratio equal to E equal to 2.7 minimum value, we can have little higher value of stage ratio to minimize the number of stages, to get delay very little small, a little larger than the smallest value, but area significantly smaller than the minimum possible value, minimum when the delay is minimum. Okay. Let me summarize very quickly. In this lecture, we have discussed various techniques for driving large capacitive load, use of super wafer, use of BiCMOS inverter, and finally, use of cascading of a number of stages, and also by using buffer sizing. Thank you very much. This is the last lecture on MOS inverters. In the next lecture, we shall discuss about complex combinational circuits. Thank you.